There are 7 chapters in Unit 2 Physics: Motion, Forces, Work, Energy and Momentum, Current Electricity, Mains Electricity, Radioactivity, and Energy from the Nucleus. The distance time graph for any object that is stationary is a horizontal line. The distance time graph for any object that is moving at constant speed is a straight line that slopes upwards. The gradient of a distance time graph for an object represents the object's speed. Speed in meters per second is equal to the distance travelled in meters divided by the time taken in seconds. Velocity is speed in a given direction. Acceleration is change of velocity per second. The unit of acceleration is the meter per second squared. Acceleration equals the change of velocity divided by the time taken. Deceleration is the change of velocity per second when an object slows down. If a velocity time graph is a horizontal line, the acceleration is 0. The gradient of the line on a velocity time graph represents acceleration. The area under the line on a velocity time graph represents distance travelled. The speed of an object is given by the gradient of the line on its distance time graph. The acceleration of an object is given by the gradient of the line on its velocity time graph, like the one shown. The distance travelled by an object is given by the area under the line of its velocity time graph. A force can change the shape of an object or change its motion or its state of rest. The unit of force is the Newton, capital N. When two objects interact, they always exert equal and opposite forces on each other. The resultant force is a single force that has the same effect as all the forces acting on an object. If the resultant force on an object is 0, the object stays at rest or at constant velocity. If the resultant force on an object is not 0, the velocity of the object will change. If two forces act on an object along the same line, the resultant force is the sum if their forces act in the same direction, or their difference if the forces act in opposite directions. The bigger the resultant force on an object is, the greater its acceleration is. The greater the mass of an object is, the smaller its acceleration is for a given force. The resultant force in newtons is equal to the mass in kilograms multiplied by the acceleration in meters per second squared. Remember, if an object is accelerating, it can be speeding up or changing direction. If it is decelerating, it is slowing down. If an object is accelerating or decelerating, there must be a resultant force acting on it. Friction and air resistance oppose the driving force of a car. The stopping distance of a car depends on the thinking distance and the braking distance. High speed, poor weather conditions and poor maintenance all increase the braking distance. Poor reaction time and high speed both increase the thinking distance. Make sure you don't mix up the two different parts that make up stopping distances. You will lose marks in an exam if you answer a question about reaction time in terms of braking distance and vice versa. The weight of an object is the force of gravity on it. Its mass is the quantity of matter in it. An object acted on only by gravity accelerates at about 10 meters per second squared. The terminal velocity of a falling object is the velocity it reaches when it is falling in a fluid. The weight is then equal to the drag force on the object. The extension is the difference between the length of the spring and its original length. Hooke's law tells us that the extension of a spring is directly proportional to the force applied to it, provided the limit of proportionality is not exceeded. The spring constant of a spring is the force per unit extension needed to stretch it. Fuel economy of road vehicles can be improved by reducing the speed or fitting a wind deflector. Average speed cameras are linked in pairs and they measure the average speed of a vehicle. Anti-skid surfaces increase the friction between a car tyre and the road surface. This reduces skids or even prevents skids altogether. Work is done on an object when a force makes the object move. Energy transferred equals work done. Work done in joules is equal to the force in newtons multiplied by the distance moved in the direction of the force in meters. Work done to overcome friction is transferred as energy that heats the objects that rub together and the surroundings. The gravitational potential energy of an object depends on its weight and how far it moves vertically. The gravitational potential energy of an object increases when the object goes up and decreases when the object goes down. The change of gravitational potential energy of an object is equal to its mass multiplied by the gravitational field strength multiplied by its change of height. The kinetic energy of a moving object depends on its mass and its speed. Kinetic energy in joules is equal to half of the mass in kilograms multiplied by the speed squared. Don't forget to square the speed when calculating kinetic energy. This is a common mistake. Elastic potential energy is the energy stored in an elastic object when work is done on the object. Momentum equals the mass times velocity. The unit of momentum is kilograms meters per second. Momentum is conserved whenever objects interact, provided the objects are in a closed system so that no external forces act on them. If a vehicle crashes into the back of a line of cars, each car in turn is shunted into the one in front. Momentum is transferred along the line of cars to the one at the front. When two objects push each other apart, they move apart with different speeds if they have unequal masses, and with equal and opposite momentum so that their total momentum is zero. When vehicles collide, the force of the impact depends on mass, change of velocity, and the duration of the impact. The longer the impact time is, the more the impact force is reduced. When two vehicles collide, they exert equal and opposite forces on each other, and their total momentum is unchanged. Seatbelts and airbags spread the force across the chest, and they also increase the impact time. Side impact bars and crumple zones give way in an impact, so increasing the impact time. We can use the conservation of momentum to find the speed of a car before an impact. Certain insulating materials become charged when rubbed together. Electrons are transferred when objects become charged. Insulating materials that become positively charged when rubbed lose electrons. Insulating materials that become negatively charged when rubbed gain electrons. Like charges repel and unlike charges attract. Every component has its own agreed symbol. A circuit diagram shows how components are connected together. A battery consists of two or more cells connected together. The size of an electric current is the rate of flow of charge. Electric current equals the charge flow divided by the time taken. The potential difference across a component in volts is equal to the work done or energy transferred in joules divided by the charge in coulombs. Resistance in ohms is equal to the potential difference in volts divided by the current in amps. Ohm's law states that the current through a resistor at constant temperature is directly proportional to the potential difference across the resistor. Reversing the current through a component reverses the potential difference across it. Remember, ammeters are always connected in series and voltmeters are always connected in parallel. In a filament bulb, the resistance increases with increase of the filament temperature. In a diode, the forward resistance is low and the reverse resistance is high. In a thermistor, the resistance decreases if its temperature increases. In a light-dependent resistor, the resistance decreases if the light intensity on it increases. For components in series, the current is the same in each component. Adding the potential differences gives the total potential difference. Adding the resistances gives the total resistance of resistors in series. For cells in series, acting in the same direction, the total potential difference is the sum of their individual potential differences. Remember that in a series circuit the same current passes through all the components. For components in parallel, the total current is the sum of the currents through the separate components. The bigger the resistance of a component, the smaller its current is. In a parallel circuit, the potential difference is the same across each component. To calculate the current through a resistor in a parallel circuit, use this equation. Current in amps is equal to the potential difference in volts divided by the resistance in ohms. Direct current is in one direction only. Alternating current repeatedly reverses its direction. The peak voltage of an alternating potential difference is the maximum voltage measured from 0 volts. A mains circuit has a live wire that is alternately positive and negative every cycle, and a neutral wire at 0 volts. To measure the frequency of an AC supply, we measure the time period of the waves, then use the formula frequency equals 1 divided by the time taken for one cycle. Sockets and plug cases are made of stiff plastic materials that enclose the electrical connections. Plastic is used because it is a good electrical insulator. The mains cable consists of 2 or 3 insulated copper wires surrounded by an outer layer of flexible plastic material. In a 3-pin plug or a 3-core cable, the live wire is brown, the neutral wire is blue, and the earth wire is green and yellow. The earth wire is connected to the longest pin and is used to earth the metal case of a mains appliance. A fuse contains a thin wire that heats up, melts, and cuts off the current if the current is too large. A fuse is always fitted in series with the live wire. This cuts the appliance off from the live wire if the fuse blows. A circuit breaker is an electromagnetic switch that opens, i.e. trips, and cuts off the current if too much current passes through the circuit breaker. A mains appliance with a plastic case does not need to be earthed because plastic is an insulator and cannot become live. Remember, the earth wire protects the user and the fuse protects the appliance and the wiring of the circuit. The power supplied to a device is the energy transferred to it each second. Electrical power supplied in watts is equal to the current in amps multiplied by the potential difference in volts. The correct rating in amps for a fuse is equal to the electrical power in watts divided by the potential difference in volts. An electric current is the rate of flow of charge. Charge in coulombs is equal to the current in amps multiplied by the time in seconds. When an electrical charge flows through a resistor, energy transferred to the resistor makes it hot. Energy transferred in joules is equal to the potential difference in volts multiplied by the charge flow in coulombs. When charge flows round a circuit for a certain time, the electrical energy supplied by the battery is equal to the electrical energy transferred to all the components in the circuit. Make sure you know and understand the relationship between charge, current, and time. Electrical faults are dangerous because they can cause electric shocks and fires. Never touch a mains appliance or plug or socket with wet hands. Never touch a bare wire or a terminal at a potential of more than 30 volts. Check cables, plugs and sockets for damage regularly. Check smoke alarms and infrared sensors regularly. When choosing an electrical appliance, the power and efficiency rating of the appliance need to be considered. Filament bulbs and halogen bulbs are much less efficient than low energy bulbs. A radioactive substance contains unstable nuclei that become stable by emitting radiation. There are three main types of radiation from radioactive substances: alpha, beta and gamma radiation. Radioactive decay is a random event. We cannot predict or influence when it will happen. Background radiation is from radioactive substances in the environment or from space or from devices such as X-ray machines. Rutherford used the measurements from alpha scattering experiments to prove that an atom has a small positively charged central nucleus where most of the mass of the atom is located. The plum pudding model could not explain why some alpha particles were scattered through large angles. The nuclear model of the atom correctly explained why the alpha particles are scattered and why some are scattered through large angles. Isotopes of an element are atoms with the same number of protons but different numbers of neutrons. Therefore they have the same atomic number but different mass numbers. In alpha decay, the nucleus emits an alpha particle, which is made up of 2 protons and 2 neutrons. In beta decay, a neutron in the nucleus changes into a proton. The electron that is created is instantly emitted. Alpha radiation is stopped by paper, has a range of a few centimeters in air and consists of particles, each composed of 2 protons and 2 neutrons. Beta radiation is stopped by thin metal, has a range of about a meter in air and consists of fast-moving electrons emitted from the nucleus. Gamma radiation is stopped by thick lead, has an unlimited range in air and consists of electromagnetic radiation. A magnetic or an electric field can be used to separate a beam of alpha, beta and gamma radiation. Alpha, beta and gamma radiation ionize substances they pass through. Ionization in a living cell can damage or kill the cell. The half-life of a radioactive isotope is the average time it takes for the number of nuclei of the isotope in a sample to halve. The activity of a radioactive source is the number of nuclei that decay per second. The number of atoms of a radioactive isotope and the activity both decrease by half every half-life. The use we can make of a radioactive isotope depends on its half-life and the type of radiation it gives out. For monitoring, the isotope should have a long half-life. Radioactive tracers should be beta or gamma emitters that last long enough to monitor, but not too long. For radioactive dating of a sample, we need a radioactive isotope that is present in the sample which has a half-life about the same as the age of the sample. Nuclear fission is the splitting of a nucleus into 2 approximately equal fragments and the release of 2 or 3 neutrons. Nuclear fission occurs when a neutron hits a uranium-235 nucleus or a plutonium-239 nucleus and the nucleus splits. A chain reaction occurs in a nuclear reactor when each fission event causes further fission events. In a nuclear reactor, control rods absorb fission neutrons to ensure that, on average, only 1 neutron per fission goes on to produce further fission. Remember, during nuclear fission, a large nucleus breaks up into 2 smaller nuclei. Make sure you know how to spell fission with 2 S's. Nuclear fusion is the process of forcing 2 nuclei close enough together so they form a single larger nucleus. Nuclear fusion can be brought about by making 2 light nuclei collide at very high speed. Energy is released when 2 light nuclei are fused together. Nuclear fusion in the Sun's core releases energy. A fusion reactor needs to be at a very high temperature before nuclear fusion can take place. The nuclei to be fused are difficult to contain. Radon gas is an alpha-emitting isotope that seeps into houses in certain areas through the ground. There are thousands of fission reactors safely in use in the world. None of them are of the same type as the Chernobyl reactors that exploded. Nuclear waste is stored in safe and secure conditions for many years after unused uranium and plutonium, to be used in the future, is removed from it. A galaxy is a collection of billions of stars held together by their own gravity. Before galaxies and stars formed, the universe was a dark, patchy cloud of hydrogen and helium. The force of gravity pulled matter into galaxies and stars. A protostar is a gas and dust cloud in space that can go on to form a star. A low-mass star. A protostar goes to a main sequence star, goes to a red giant, goes to a white dwarf, and finally to a black dwarf. In a high-mass star, a protostar goes to a main sequence star, to a red supergiant, to a supernova, to a neutron star, and to a black hole if there is sufficient mass. The Sun will eventually become a black dwarf. A supernova is the explosion of a supergiant after it collapses. Elements as heavy as iron are formed inside stars as a result of nuclear fusion. Elements heavier than iron are formed in supernovas as well as light elements. The Sun and the rest of the solar system were formed from the debris of a supernova.